Howdy, this is the video digest for the 6th week of the APCH 640 class. The topic of the week is physical activity, fitness, and disease. In general, prospective cohort studies were used to determine the association between physical activity or fitness and various health risks. Physical activity was measured in diverse ways. Maybe it was measured in terms of energy expenditure based on activity, its mode, duration, frequency, and intensity. The cardiovascular disease was measured as coronary heart disease, cerebrovascular disease, or cardiovascular-related mortality. According to Sharma and Lee 2010, when most active ones were compared with the least active ones, the median risk reduction was about 30% for men and 40% for women. And the biggest decrease in the risk was observed between the low-level physical activities with the moderate physical activities, and the least changes was observed between the moderate and the high physical activity levels. For instance, in a Harvard alumni study, which was a prospective cohort study that followed about 7,000 men for 6 years, the researchers estimated the amount of energy expenditure based on the self-reported physical activity and adjusted relative risk for coronary heart disease. The study showed that the biggest decrease in the relative risk was observed between the less than 1,000 kilocalories per day with 2,000 kilocalories per day. The risk remained almost steady until really high physical activity level was reached. According to 2008 physical activity guideline, at least 150 minutes of moderate physical activity or 75 minutes of vigorous physical activity per week are required. However, there are various diverse results out there about how much physical activity or exercises are actually required to see a significant health benefit. And some even says that about 2 minutes per day 2 minutes of high-intensity interval trainings per day or 5 to 10 minutes of slow running per day are sufficient. So what this recent studies implies that maybe less than the required amount by 2008 physical activity guideline is sufficient. The terms cardiorespiratory fitness and physical activities are typically used interchangeably, but they really shouldn't be. Physical activities is generally a self-reported variable, such as by asking, how frequently have you been engaged in a moderate physical activity in the past week? The cardiorespiratory fitness, the CRF, on the other hand, is generally a lab-measured variable, usually in terms of metabolic equivalence, the MET, or maximal oxygen uptake. Traditionally, maximum heart rate is estimated by deducting one's age in terms of years from 220. The common target heart rate is measured using Carbonen formula. Technically, 1 MET equals to the amount of oxygen consumed while sitting at rest, and it equals to 3.5 milliliter of oxygen per kilogram body weight for every minute. According to the meta-analysis by Kodama 2009, each 1 MET increase in CLF, which corresponds to 1 kilometer per hour speed of jogging or running, can reduce about 13% all-cause mortality and 15% of cardiovascular disease. Using the reference from the Physical Fitness Specialist Certification Manual 1998, a poor MET for a 50-year-old man would be 8 and it would be 6 for women. The CLF can be influenced by multiple factors including genetics, physical activity, age, gender, body composition, especially the fat mass, and mode of exercising, etc. So according to the Heritage Family Study, there was a significantly greater variance between families rather than within families. The maximum heritability estimate of the CLF response to the training reached 47%. In the ACLS, low fitness level was determined by the lowest 20% of age-sex specific distribution of exercise duration in the overall study population. For the given statement, I would say it depends. The mortality will be least for who are fit now and who remains fit, and the relative risk of mortality will be higher, a little higher than that for those who are fit now but becomes unfit, or who are unfit now and who becomes fit. But if the person, and will be the relative risk for mortality will be highest for those who are unfit now and who remains unfit in the future. So when the nerve impairs the action potential reaches the axon terminal, it triggers the influx of calcium ions into the axon, and influx of calcium into the axon causes synaptic vesicles to release acetylcholine via exocytosis, which then diffuses across the synaptic junction. When acetylcholine binds to the acetylcholine receptors on the sarcolemma, it opens voltage-gated channels which allows in sodium ions. And when sodium rushes across the sarcolemma, the charge along the inner membrane becomes less negative, and this is called depolarization. So when depolarization reaches a certain threshold, the action potential propagates along the sarcolemma. An action potential is conducted into the interior of muscle fibers through an infolding of sarcolemma, known as transverse tubules or T-tubules. The calcium-storing membranous network inside the muscle cell is called sarcoplastic reticulum or SR. So when activated, voltage-gated proteins connecting the T-tubules and the SR cause the release of calcium from sarcoplasm. Release of enzyme acetylcholinesterase in the neuromuscular junction destroys acetylcholine and stops the generation of muscle action potential. The functional unit of muscle contraction is called sarcomere. In terms of filament thickness, actin filament is the thin one and myosin filament is the thick filament. The first step of sarcomere contraction is when calcium binds to troponin. Activating the myosin head occurs when ATP combines with myosin head and is hydrolyzed to ADP. The power stroke occurs as ADP is released and myosin head pivots. Thin myofilament slides towards center of sarcomere. The binding of another ATP to the myosin head causes detachment of the myosin head from actin binding. By the way, a deficiency of ATP in death causes rigor mortis, failure of myosin to reset. The end of contraction, calcium ions returns to the sarcoplasmic reticulum. Endothelial shear stress is the tangential force derived by the friction of the flowing blood on the endothelial cell surface. And high or low endothelial shear stress is associated with health. For example, atherosclerotic lesions can form at the arterial region where low and oscillatory endothelial stress occur. There are multiple detectors of shear stress on epithelial cells, and direct detection may occur through glycocalyx, which unfurls under shear stress, and the signal can be transmitted to the intracellular domain through cytoskeleton. And various ion channels such as calcium channel, potassium channel, and chlorine channels are known to be responsive to the shear stress as well. And upon the act of shear stress, rapid phosphorylation of tyrosine kinase receptors occur in a ligand-independent manner, and if the required cofactors for the ENOs present, the phosphorylated protein kinase can activate the ENOs to produce nitric oxide. And production of nitric oxide is important that it can increase the delivery of oxygen and nutrients to the tissue and reduce blood pressure and exert inhibitory effect on inflammatory processes and smooth muscle proliferations on the blood vessels. So low endothelial shear stress has multiple important physiological effects. That includes the reduced bioavailability of nitric oxide, increased production of reactive oxygen species, and oxidation of low-density lipoprotein. So many older adults suffer from their reduced capacity to initiate and maintain sleep. And a recent study by Melancon 2015 investigated the effect of exercise on sleep quality among all the adults. So it was a prospective cohort study that involved 13 Canadian men who were at ages between 57 and 70 years old. They measured their sleep quality in terms of depth and continuity using the polysomnography. They did a measurement of total of 6 nights, 3 nights before the 16 weeks of aerobic training, and 3 nights after the training. So, and then also at the last day of each 3 nights of recording, they asked participants to participate in an hour of acute exercise, which was an hour of moderate exercise. So their studies show that the acute exercise followed by 16 weeks of aerobic training improved the sleep quality by reducing the wake time by 30% and improved the slow wave sleep by 71%. They also noted that the acute exercise was the key influencing factor on their slow wave sleep changes rather than the 16 weeks of exercise training, the aerobic exercise trainings. So the study in overall agreed with the previous studies that exercise has a beneficial effect on the sleep quality among all the adults.